Hello, good day everyone. Welcome to the first lecture of the Machine Design Line. And the outline of our lecture today is about the analysis of simple stresses. So we have three lessons under the module 1. First lesson is the tensile stress, followed by the compressive stress, and thirdly is the shear stress. So in total, the module 1 will discuss all about the simple stresses, about the designing and all the other parameters that should be discussed, including the introduction of machine design, the loads, and the modulus of rigidity and elasticity. In engineering practice, the machine parts are subjected to various forces, which may be due to either one or more of the following. So first is the energy transmitted. So we all know that when machine parts are enmeshed with each other, uh, it has the purpose of transmitting motion. So not only does it transmit motion, but also the energy. So when there is energy transmitted between machine elements or machine parts, there's also forces that are acting upon these machine parts. Second is the weight of the machine. Yes, the machine itself exerts loads on the machine parts because of the influence of the gravity, thus the weight of the machine. Next are the frictional resistances. Yes, due to the fact that these machine parts are meshing or in contact with each other, it is expected by fact that there are frictional resistances between these machine elements. And fourth is the inertia of reciprocating forces. Whether it's reciprocating or oscillating motion of parts, we can expect that there is an inertia developing on these machine elements. Thus, with this inertia, we can expect that there are forces that are acting between these machine parts. Fifth is the change in temperature. We all know from our mechanics lecture that thermal stresses causes the machine part or any structural part to exert force with another element uh, that it is in contact with. And lastly is the lack of balance of moving parts. The different forces acting on a machine part produces various type of stresses. Yes. So in this chapter or in this module, we'll be discussing different types of stresses. Okay. So what are loads? It is defined as an external force acting upon a machine part. Okay. So and there are various classifications of loads, and this classification is important in the preceding lessons or modules, because this type of loading will determine on how shall we analyze, on how shall we design this particular machine parts. First is the steady load. A load is said to be dead or steady if it doesn't change in magnitude or direction. So what are examples of dead or steady loads? So an example of a dead or steady load is, for example, is the weight of a building structure elements such as beams, walls, roof, and structural flooring components. And this is and well in touch with uh, in machines. These are the static or static portions of the machines that, through their weight, it exerts forces in the machine. Next is a live or variable load. So it is said that a load is a variable load uh, when it changes continually. So what are examples of live loads? So live loads, since it varies over time and often result from occupancy of the structure, uh, it may include if there are users, people, action of wind and fan elevation, uh, weight of uh, weight of some materials or things over a machine. Yes, as long as this type of loading changes continually, it is the direct opposite of the first classification of load. Third is the suddenly applied or shock load. So a load is said to be suddenly applied or shock load if it is applied or removed suddenly. So what are examples of shock loads? So examples of shock loads are uh, any actions made towards a machine, any action towards machine part that, yeah, for example, if there is a particular machine or another part that is applied suddenly or even removed on your machine element, this is considered a shock load. Impact load. So you know impact load is a load that is applied with some initial velocity. So in comparison with shock load are loads that are suddenly applied with no initial velocity. While impact loads have initial velocity when applied to a particular machine part. Okay, so let's talk about stress. Okay, so let's take a look at this figure at the far right of the presentation. In some external system of forces or loads act on the body, the internal forces, so equal and opposite internal forces, set up at various sections of the body. For example, of on this given body, resist the external forces. Okay, so when a force, any type of force or loading applied to the body, there are internal forces within the body that by virtue of the third law of motion, there will always be equal and opposite corresponding internal forces that tries to resist external forces acting on the body. Now this internal force per unit area at any section of body is known as unit stress or simply stress. And it is denoted by a Greek letter sigma. So this is a Greek letter sigma, which will be you'll be encountering throughout this course, and which we will use in your next years when dealing with stresses. So mathematically, the, the stress or sigma is equal to the force or load acting on body over the cross-sectional area of the body. So it is mathematically sigma is equal to P over E. So where P denotes the force acting on the body, and A and capital A is cross-sectional area of the body. So looking to the units of the force and the cross-sectional area, we can see that the unit of stress, specifically in the SI units, is equal to 1 Newton per meter squared, where Newton is the unit used for force, and meter squared is for standard used unit for area. and thus it is equivalent to 1 Pascal. So 1 Pascal is equal to 1 Newton per meter squared. Okay, but in actual practice we use bigger units of stress such as the MPa and GPa. So 1 MPa or the megapascal is equal to 1 million Newton per meter squared, or it is equivalent to 1 Newton per millimeter squared. And 1 GPa or 1 gigapascal is 1 billion Newton per meter squared, or 1 kilonewton per millimeter squared. So you will be encountering these units more often or even always in the mix and throughout this course. Yeah, when we are designing the machine elements. All right. So next up is strain. So when a system forces or loads act in a body, it undergoes some deformation. Okay. So here we cannot generally assume the rigidity of the body when it is applied with some forces. So when we mean with rigidity, it doesn't undergo deformation, unlike with your previous courses as in the machine elements 1 and 2, where where the course where the courses were only dealing with motion and not with the forces applied in the body. Thus the machine parts or machine elements were assumed to be rigid. Thus when we mean with rigid, it doesn't undergo any distortion or deformation. Here in the study of machine design, we consider we consider the deformation of a body. Okay, so when we consider the deformation of the body, when there are applied forces on it, it undergoes some deformation, whether there will be elongation or shortening of a body, depending on what type of loading is applied on it. So unless the deformation per unit length is called unit strain or simply strain. So looking into this figure, you can see that there is an external force applied on this body. So denoted by F. So there's external forces. So we can see apparently that these forces applied tends to elongate the body. So when we say it tends to elongate, thus the deformation, there is a deformation that tends to increase the length of the body, such as before the application of force. We have the initial length. We have the initial length denoted by L naught, and upon applying force, external force that tends to elongate the body, there's a deformation denoted by delta L. So nagkataas siya, no? So it tends na nagkataas ang atong body. And finding the deformation per unit length is called unit strain. So strain, since it is a deformation per unit length, it is delta L over the initial length. Okay, so basically unit strain or strain is a dimensionless parameter. Okay, so mathematically, strain is denoted by the Greek letter epsilon. Epsilon, this Greek letter, which is equal to the division of the delta L over L, where delta L is the change in length of the body over L, which is the original length of the body. Okay. So let's after since we have already discussed about the stress and strain, we'll talk about the different stresses. So first of our discussion is about tensile stress. Okay. So when a body is subjected to equal and opposite eggshell pulls denoted by P or tensile load, then the stress induced at the intersection of the body is called tensile stress. So let's look these pictures in this presentation. Okay, so looking at this body, there are forces applied to this body. So let's look at this. The forces are applied externally away from the body. So this P denotes the forces that are equal and opposite. Okay. So in vernacular, we can makita natin diri that there is letter P acting with this body is pabira, di ba? So it tends to elongate the body. So when we tend to elongate a body, it causes tension. Thus, the name of the stress caused into the body is called tensile stress, right? So mathematically, the ratio of the increase in length to the original length is known as tensile strain. Okay, so we talk about tensile stress, uh, which is the resistance of the body against the forces that are equal and opposite that tends to eliminate the body. It has a corresponding increase in length in ratio with the original length, which is the tensile strain. So mathematically, the tensile stress, which is represented or denoted by sigma sub t, is equal to the force over area. So force over cross-sectional area, alright? And the tensile strain, epsilon sub t, is equal to the uh, deformation over the original length. Okay, so where the force is the tensile force acting on the body, and A is the cross-sectional area of the body. So cross-sectional area of the body is the area of the plane that is uh, is the area of the plane opposite to the acting force. Alright? So this cross-sectional area, kung asa to gi-apply itong nga force katong nga area nga sa katong cross-section is mo to siya ang our concerned nga area in computing the tensile stress. Okay, and for L is the original length of the body. So original length of the body is the length of the body before a force is applied or before the tensile force is acted on the body, and the increase in length is the deformation after the body is active, after the force is active in the body. Right. So let's go with this example problem. Okay, so equal chain of a crane required to carry a maximum load of 50 kilonewtons is shown in figure below. Find the diameter of the link stock. The permissible tensile stress in the link material is not exceed 75 megapascal. Right, so uh, let's take a look at this the figure. So chain o kanina sa crane is required to carry maximum load of 50 kilonewtons. Okay, so the material of the link stock or the link has a permissible tensile stress that is designed not to exceed 75 megapascal. So from those given stress and maximum loading, we are required to find uh, the diameter of the link stock, right? So we have given values. We have been given this problem the maximum load, which is equal to 50 kilonewtons or 50,000 newtons, and the permissible stress or maximum stress for the link stock is 75 megapascal or 75 Newton per millimeter squared. So let's let's take D as the diameter of the link stack, which we are required to compute. And thus, from that, the cross-sectional area. So the cross-sectional area of the link stack, we all know is a circular area. Uh, thus the formula that we'll be using in finding the area of the if the cross-section is the area of a circle. So pi over 4 times the diameter, square of the diameter. Okay, so we have the area, which is equal to 0.7854 d squared. So d squared is still unknown here since this is the requirement of this problem. Okay, so while you are watching, please get a note, a pen and paper, so you can solve this simultaneously as we go on uh, with this problem. Okay, so next, we are given the maximum load P. So the maximum load P given is the 50,000 Newton. Okay, so let's look at this, the first line of the first line, where P is equal to sigma sub T times A. So do you remember what is this formula? This is the formula for the stress, right? So where we so from this we substitute the values. So P is the maximum load, which is equal to 50 times, which is equal to 50,000 Newton. Then we substitute uh, in the value for sigma sub T, which is the maximum permissible maximum stress, is equal to 75 MPa. So we all know that 75 MPa is equal to 75 Newton per millimeter square. Thus, we are just substituting it directly in the second line, times we multiply it with the value of the area, or the relation of the area that we had just solved previously. So this is equal to 0.7854 d squared, right? So further evaluating this, we've got the value of 50,000. Yes, 50,000 here is equal to 58.9. Okay, so please check this, or verify this using your calculator. So therefore we get the diameter, the diameter of the link stack using this proceeding calculation. So here, so from this line, we get the d squared is equal to 50,000 divided by 58.9. So we'll get the square root of the evaluated value. Then we get 29.13. So 29.13, we round this off the uh, nearest tense value. So say that the required diameter of the link stack is 30 millimeters. So our final answer is 30 millimeters. So it's okay. In the I will not be strict with the with the with using the rounding off of answers, but I may set in the following starting to module 3 to implement the rounding off of answers to the nearest value to the standard sizes. Okay, so since these values are since we when we are dealing with designing, we have to find the answer that is that is nearest to the standard sizes, so that it is convenient for us to find the values, uh, the nearest to the standard values, right? Let's proceed with the compressive stress. Okay, so compressive stress is when a body is subjected to two equal and opposite axial pushes or compressive loads, the stress induced at any section of the body is called compressive stress. Okay, let's take a look at this figure. Uh, the forces denoted by P in this figure are applied uh, going into the body. Okay, so these are two equal and opposite pushes. Okay, looking back at the first type of stress, which is the tensile stress, the two forces, equal and opposite, are applied uh, are applied from mm, from the center of the body. So the with tensile stresses, with tensile stress, the applied loads tends to elongate, and they are axial pulse applied. So compressive the application or the way compressive loads are applied is the exact opposite of the tensile loads. Okay, while the while the tensile loads tend to elongate a body, compressive loads tend to shorten the body. Okay? So, kung ano siya, patulog ni siya, no? Tulog ang application ni si aning sa mga compressive loads. While ang atong tensile loads is pabirap sila. So, the tensile load tends to elongate the body, while ang compressive loads is it tends to shorten the body. So, the stress or the resistance of the body against this type of loading at any section of it is called compressive stress. Okay. So naapit siya ay corresponding strain upon the application of those loads, which is called the tensile. Sorry, this is compressive strain. Okay, so this is compressive strain is denoted by epsilon sub c, which is equal to the change in length delta L over L, right? So currently there is a compressive strain. The change in length is the decrease in length after applying the compressive loads. Okay, and the compressive stress, um, the sigma sub c is equal to the compressive load applied over the cross-sectional area of the body. Okay, so the same with the tensile stress, we have the PA, L, and delta L denotes the compressive force acting your body. Uh, it can be a unit of Newton or other units of force. Uh, A is the cross-sectional area of the body, so the area of the plane toward the um, opposite or normal where the force is applied. It can be a unit of meters squared. And length is original length of the body width, and also the increase in length, which can be represented by using the units of length such as meter. Right. So let's proceed with the Young's modulus or modulus of elasticity. Okay. So we will know about Hooke's law. So Hooke's law, we have this is a review, and I'm confident that you have already encountered about Hooke's law in your mechanics course. So according to Hooke's law, when a body is loaded within elastic limit, the stress is directly proportional to strain. Right. So when we say directly proportional, the stress is directly proportional to strain. It can be represented mathematically by this equation. So the stress or the sigma is proportional to epsilon. Okay, so let's put this into an equation form. So we have uh, the sigma or stress is equal to some constant of proportionality times the epsilon or the strain. Okay, so by this proportionality equation, we are using this we are introducing a new variable or a constant of proportionality. So what is this constant of proportionality? So the constant proportionality from Hooke's law is uh, what we call as the Young's modulus or modulus of elasticity. Okay, from this, okay, no. Therefore, from this equation, we can derive the constant of proportionality E is equal to the ratio of the stress over the strain. So we all know that by further dissecting this ratio, please check now if you are having a notes, a pen and note right now. Please verify this equation. Okay, please follow this on how this this equation in the rightmost part is derived. Right. So we all know that the stress is equal to the ratio of the force and the area. Thus we have P over A. And uh, the epsilon or the stress is the strain is equal to the ratio of the delta L over L. Okay. So when we divide this, it transform na manipulation of this equation na mo siya nga E times L over area times delta L. Right? So balik this capital E is the constant of proportionality from the Hooke's law or the Young's modulus or modulus of elasticity. Okay. This modulus of elasticity is typically expressed in GPA in the SI units, GPA or the Pascal unit. Okay. So let's remember that Hooke's law holds good for both tension and compression types of loading. Okay. So what's the significance of knowing this Young's modulus? So for example, we have a table here of the modulus of elasticity of commonly used engineering materials. So the materials listed here in this table are the steel and nickel with a GPA of 200 to 220 GPA. With the wrought iron, 190 to 200, cast iron and copper, plus aluminum and timber. So these are the corresponding modulus of elasticity. Okay. So sa may significance sa modulus of elasticity. So uh, if we go back to the equation derived from Hooke's law, uh, the higher uh, the higher the value of the modulus of elasticity, the more it tends to be more rigid. Okay. So since from this equation, the E is equal to the P times L over A times delta L. It means that it has a very low deformation. So magkataas ang value sa modulus of elasticity. It means nga dili siya basta-basta nga ma-deform. Walay lingon siya, dili siya basta-basta na deform. Okay? So while you're increasing with stress of the body reacting upon a force applied, gamay ra ang iyang strain. So gamay ra ang iyang deformation per unit original net niya. So this table indicates nga mataas ang mga value nila is dili Dili basta-basta ma-deform. So for this is the highest modulus of elasticity in this table is the steel and nickel. So dili pinaka more rigid ang steel and nickel versus the timber or the aluminum. Alright? Okay. So let's look at this example problem. So this example problem is a hydraulic press exerts a total load of 3.5 meganewton. And this load is carried by two steel rods supporting the upper head of the press. If the safe stress is 85 megapascal and E, or the modulus of elasticity, is equal to 210 kilonewton per millimeter squared, find 1. The diameter of the rods, and 2. Extension is rod in a length of 2.5 meters. Okay, so we have this problem is we have a hydraulic press exerting a total load of 3.5 million newtons, and this load is carried by two steel rods. Okay, so we are required to find the diameter of the rods and the extension or change in length in each rod, given a initial length of 2.5 meters. Right. So we are given the load or denoted by P equal to 3.5 meganewton or 3.5 million newtons. We have the sigma sub T, or the tensile stress, maximum tensile stress of 85 megapascal or 85 newton per meter squared. Okay. First off, how did we determine if this type of stress is tensile and not compressive? Okay. So this since it exerts it exerts a loading of 3.5 meganewton. So since this there's two steel rods, since this is carrying the since the load is carried by two steel rods, so consequently nagbitay niya itong load of 3.5 meganewton. So because of that, we can safely assume that this type of stress the type of stress like exert from this load is it tends to elongate the two steel rods. Okay, so direta na kayo nung so first off, when tackling with problems, for example, with these simple stresses, first off it is important to visualize it kung saan na type of stress, because it may the constant factor, for example, in the calculation of the deformation. Okay, so when you assume compression na siya, pili nga ang final lengthening after applying these forces na since it tends to shorten the body, imo siya minus sa original length. While kung it is intensile, if you assume or wrongly assume na tensile ang force applied in the body, imo siyang since the forces tend to elongate the body, you add the deformation to the original length. Okay, so it is important in tackling this type of problems to first determine if what type of loading is exerted on the body, right? So here we have determined by inspection, by inspection, by determining of that since the load is carrying, since the load is carrying the load, so we are sure or we are confident that step loading is uh, tensile loading. Okay, and also it is also given in this problem, no? It's also given in this problem that uh, in the second requirement there is extension. So apparently this means that this type of loading is tensile loading, since it requires what is the extension or the elongation. All right. So next is we are given with the modulus of elasticity, which is equal to 210 kilonewton per meter squared, or 210 GPa, and we have an initial length of 2.5 meters or 2,500 millimeters. So we are required to find the diameter of the rods and the elongation or extension of this rod given this initial length. Alright, so first off, we'll find the diameter of the rods. So let's take D as the diameter of the rods in units of millimeters. So from that, we find the area. Okay, so the rods are in circular shape. Circular shape. Thus, the formula for getting the area is equal to the area of a circle. So we find uh, the area, which is equal to pi over 4 times d squared. Okay, the load is carried by two rods. So meaning each rod, each rod is uh, each rod is carrying half of the total load, right? So for one rod, it is carrying one half of the total load. Okay, so did you get why we are dividing the load into two? Okay, so because there are two rods, so for each rod it carries a one half of the 3.5 million newtons or 1.75 uh, million newtons of loading, right? So we know that the load carried by each rod P is equal to 1.75 times 10 to the power of 6 newtons. Then we will compute the diameter from the equation of stress. Okay, so this equation is we get this equation from the basic equation of stress, which is equal to sigma sub t is equal to force over area. So since we know about the force applied, force or applied or carried by each rod. So it is 175 million is equal to delta sigma sub t times area. Okay, so we get the area. So can you area, we just have to simply uh, divide pi over 4. So we divide pi over 4, this 0.7854 d squared, right? So please follow this by computing in your own right now. On your own right now using your pen and paper. Then what did we get is 85. So 85 is given value of the maximum or safe stress. So it is in the unit of 85 Newton per millimeter squared, right? So times 0.785 for d squared. So in the next line is we further evaluate 85 times 0.754, which is equal to 66.76 d squared. Okay, so therefore we further compute this square, which is equal to, from this value, 1.75 times 10 to the raised to the power 6 over 66.76, right? So we get, upon evaluating this, we get 26,213 d squared. So finding the square root of 26,213 is equal to 162 millimeters. Okay, so therefore a final answer for the diameter of the rod is equal to 162 millimeters. So this is a final answer. So uh, the two rods, which is carrying a total of 3.5 uh, meganewtons, which is equivalent to which you are carrying 1.75 meganewtons of load. We get the area of 100. I mean, we get the area of sorry, we get the diameter of the rod equal to 162 millimeters. Okay, so our second requirement is the extension in its rod. So when we mean extension, this is delta L in its rod, uh, upon carrying the load. Right. So delta L, let's take delta L as the extension in its rod. Okay. We know the Young's modulus. So we know the Young's modulus. So can Young's modulus uh, given in the problem. So Young's modulus for the material of the rod is equal to 210 kilonewton per millimeter square. So it's solved for the uh, delta L using this equation. So this equation, you have encountered this equation in the previous slides, which is derived from the ratio of the stress and the strain. Okay, so this further we further evaluate that P sub P over A is equal to the tensile stress, right? Kani? Imo siya kani evaluate na to then not the initial length, L over delta L. Okay, so we know that these values, sigma sub t is given, and also the initial length, right? So we simply multiply these values 85 Newton per millimeter square times 2.5 times 10 to the power of 3. So ganun i-command natin gimotor nato siyang 25 because the unit of this is for the consistency of units. Since the units kaning 85 is 85 Newton per millimeter square, ato siyang multiply by unit of millimeter po sa initial length divide. Then all over delta L, right? So for the evaluating it, we get 212.5 thousand over delta L. Okay, so let's get so we have the delta L is we divide 212.5 thousand over 210,000. We get the illumination extension which equal to 1.012 millimeters, right? So do a review. Please do a review of the problems by solving it by yourself and verify in your own solution uh, kung sakto ba ang process sa solve ninyo, and you should get these final answers of the diameter equal to 162 millimeters and for the extension equal to 1.012 mm. Alright, so please do a review of not only this problem but also the previous problem and the tensile stress. Alright, let's proceed with shear stress. Okay, so shear stress, when a body is subjected to two equal and opposite forces acting tangentially, so acting tangentially across the existing section, as a result of which the body tends to shear off. Okay, so let's first take a look at this figure. Right. So we have two equal and opposite forces. So first, let's take a look at this force at figure A. All right. So initially we have this body. So we have this body now. It could be this is obviously a rivet connection of two plates, right? So two equal forces denoted by P are applied. So these forces are equal and opposite applied sa atong body. Okay. Upon application of these forces, it tends to shear off the section. Okay? So tanawa na to ni siyang kanang libet na to diri, no? It tends nga maputol. Maputol niya nga itong kuan diri. It tends nga putol ang atong libet diri. Right? So we can see here that there's a tendency to cut off or to shear off this particular section. Okay? So this type of stress that's acted upon this particular arrangement is called shear stress, right? So just like with tensile and compressive stress, it has also a corresponding strain, which is also the shear strain. Okay, and the shear strain is measured by the angular deformation accompanying the shear stress. Okay, so let's first take a look at the mathematical formation of the shear stress. So shear stress is represented by Greek letter tau. So Greek letter tau is equal to tangential force over the existing area. So sa itong tangential force, these tangential force are the forces denoted by T in the previous slide. Yes, here these are the tangential forces, and what is the resisting area? Okay. So you might be confused what someone ang resisting area for this particular arrangement. Okay. So let's take a look at this back at the two figures. So what area is sheared off? That tends to be sheared off when applying shear. When applying these forces. So the resisting area is equal to the area of the cross section of the rivet. So thus, because it has these rivets have a cross section of circle, therefore we have the equation of the resisting area equal to the pi over 4 times d squared. Okay. So kani siya, no? I know you have encountered this particular arrangement in your first year and second year courses ninyo. So consider a body consisting of two plates. So not ito ka plate diri, no? Ka plate 1 diri sa upper plate, or na tay kaduha nga plate diri sa ubos kanang apply na di kaduha force. Connected by a rivet. So kanina gi-rivet na sila kung duha ka mga plate na to. Right? So in this case, the tangential force P tends to shear off. So birahon mo tong duha ka gap, isumpay mo ng mga plates, no? Two equal but opposite forces. Isa na metabo, it has the tendency na maputol ning rivet. Right? So given dili na to ma-elongate katong sa part sa plate. Ang section nga atong i-consider diri with shear stress is katong section nga connect sa duha. So mo na ang rivet, diba? So kung pamasdan mo, so have a tendency nga maputol nimo ang rivet. Okay. It may be noted that when the tangential force is resisted by one cross section of the rivet, or when shearing takes place to one cross section of this rivet, then the rivets are said to be in single shear. Right? So, what's about single shear? So, single shear, isa ra ka part sa atong rivet ang maputol. Alright? So, isa ra ka kandidi sa atong muna siya gitawag single shear. If there is isa ra ka ang shearing only takes place at one cross section, sister cross section, right? So may atong single shear. Okay, so mathematically, if you take a look at the area of the shared section. So muna siya ang cross section sa tulog dito, which is equal to the formula for the area of circle. So pi over 4 times d squared. Okay. So ang atong shear stress at the rivet cross section, using the same formula for stresses, the shearing stress tau is equal to the applied force over the rivet cross section. Okay. So let's substitute the equation for the rivet cross section katong nasa previous slides. So we have p over pi over 4 times d squared, right? So we have this the basic equation for shear stress. For single shear is equal to 4p over pi d squared, right? So may ang para sa single shear. Okay. Now let's consider three plates connected to each other by rivet. Alright. So paano? Let's look at these figures. So there are two plates connected by the other two cover plates. So in this case, the tangential force P tends to shear off the rivet at two cross sections. Okay. So first is muna siya initial na tong perform sa kaning nga arrangement. Upon applying or after applying force P sa kaning arrangement tends to shear off at two cross sections sa rivet na to. Okay, so nakita natin nga doon cross section, no? Okay. It may be noted that when the tangential force is resisted by two cross sections of the rivet, or when the shearing takes place at two cross sections of the rivet, na natin yung cross sections din, then the rivets are said to be in double shear. Okay, so it involves shearing of two sections sa rivet. Therefore, this is called the double shearing. So in this case, the resisting area consisted of this particular equation. So we have this equation which is equal to, since nag-involve ng tatluha ka cross sections resisting the shear is equal to the two areas. So we need two areas 2 times the formula of the cross section. So 2 times pi over 4 times d squared. Okay, so this is for double shear. And the shear stress is therefore from the equation in getting the stress, the shear stress tau is equal to P over A. So substituting the relation of for the resisting area P over 2 times pi over 4 times d squared. So we have this, we have to further simplify. We get, so na siyang 1/2 pi times d squared. Therefore, the equation in getting the shear stress for double shear is 2p over pi d squared. Okay, so do you see the difference between double shear and single shear? So for the double shear and single shear, I think you have understood or you get the concept why it's single or double shear. Then how we derive the equations for their corresponding shear stress. Okay. So there are notes that we should remember kung kano sa ta maka-assume kung saan ta maka-assume kung double shear ba ni siyang particular arrangement. First is if all lap joints and single cover butt joints are in single shear, while the double butt joints with double plates, okay, double plates are double shear. Okay, Basta, yung concept na if duha ka part o duha ka section din sa rivet is multi siya i-tense nga, multi siya maputol. Or ito part to siya ma-shear, ito na siya. Is multi siya shear. Alright, is, second is in case of shear, the area involved is parallel to the external force applied. Right? So, comparing with the first two type of stress, the tensile and the compressive stress, the area of interest in solving the tensile and compressive stress are the areas which are normal to where the force is applied. Okay? So, mo siya nga construction, no? Since mo siya normal or opposite, kung saan ito i-apply ito, either the tensile or compressive load. While there is a shear, the area is parallel. The area is parallel. Kung saan mo i-apply ang katong first. Diba? So we can see, as I've been seeing in the previous slides, nasa shearing, we deal with the area of the rivet na parallel siya kung saan natin i-apply ang force. Right? So parallel for shearing, while for the tensile and compressive loading, ang computation sa stress or ang area of interest na to dito is mo to siya ang opposite nga or normal or opposite nga area sa diaphragm force. Third is when the holes to be punched or drilled in the metal plates, then the tools used to perform the operations must overcome the ultimate shearing resistance of the material to be cut. Okay? So area sa mga area na, for example, kung mag-punch ka, or you tend to make a hole out of a body. So sa man tong sa mga area tong parallel kung asan mo apply tong force. Right? So mo to siya ang area of interest when we are punching a hole sa skeletal plate or sa body. Then, and also, when doing so, it must overcome the ultimate shearing resistance of the material. Okay. So, in line with that, if the whole diameter D is to be punched in a metal plate of thickness T, then the area to be sheared is equal to the area pi D times T. Okay? So, man siya pi D over T. Pi D times T. Okay. So, last tayo imagine na tayo sa plate. O plate nga of thickness T. So, na tayo i-punch na hula na niya. So, i-punch na hula niya is in direction niya is ang direction sa force is going down. Thus, the parallel na area to niya is equal to the area of the circumference times thickness. Okay? So, ang area to be sheared nila is dili itong area sa circle na. For example, kung mag-imo ka o circular na hole sa plate, ang area nga yung i-consider na to or interest area na to sa shearing na to is dili ang circular na area, kung dili ang area ito na sa gilid. So, kung area on the side is equal to the circumference of the circle times thickness. Thus, the area to be sheared when we are punching a hole is equal to pi d times t. Okay, and the maximum shear resistance of the tool or the force required to punch a hole out of that metal plate is equal to the. So kaya asa mo ito So this is from tau shear stress is equal to P over A. Thus, we get that the force applied is equal to the area times the shearing resistance. So, Substituting the relation of area and this equation, we have pi d times t times tau. Then, where the tau sub u is the ultimate shear strength of the material of the plate. Okay. Next is we have another constant of proportionality with regards when considering Hooke's law. This is called the shear modulus or modulus of rigidity. It is it has been found experimentally that within the elastic limit, the shear stress is directly proportional to shear strain, right? So we got this particular relation from an experimentation that this is it's supposedly uh, a notation for uh, proportionality. So tau is proportional to the shear strain, or tau is equal to the C, or the constant of proportionality, times the shear strain. So from this is we got that uh, a relation of the C, or the constant of proportionality, is equal to tau over phi. Okay. So what is the C? So C is what we got from the proportionality relation of the shear stress and the shear strain. So thus we have the shear modulus, or the modulus of rigidity. Okay. So from this is the tau represents the shear stress, phi denotes the shear strain, and C is the constant of proportionality from that relation, or is known as the shear stress, shear modulus, or modulus of rigidity. It is also denoted by capital N or G, right? Just like with modulus of elasticity, there are also tables, like this table of the modulus of rigidity of some of the commonly used materials in engineering practice. For example, of these materials are steel, wrought iron, cast iron, copper, brass, and timber, with modulus of rigidity corresponding to these values you see here. Okay. So looking to this equation, the higher the values of the modulus of rigidity uh, indicates the indicates the that the material uh, doesn't tend to uh, doesn't tend to have a deformation when applied with shearing loads, right? So mas magaling kung ang usa ka body nga taas og modulus of rigidity uh, compared sa katong lower. So thus steel when applied with shearing load is more rigid, or has given the same force, has lower deformation than the timber, which has lower value of modulus of rigidity. Okay, so let's take a look at this example problem. So let's take a look at this problem. This is a simple problem of punching a circular hole out of a metal plate. So calculate the force required to punch a circular blank of 60 millimeter diameter in a plate of 5 mm thickness. Okay. The ultimate shearing stress resistance of the plate is 350 Newton per meter squared. So in this problem, we are required to calculate the force to punch a hole or a blank of 16 millimeter diameter. Right. So we are given with diameter of the hole, which is equal to 60 mm. Thickness of the plate is 5 mm, and the maximum shearing resistance of the plate is equal to 350 Newton per millimeter square. So now we will calculate the area under shear. So you will know when we are punching a hole that the area resisting the shearing load is uh, equal to the circumference of that hole times the thickness. Okay, so we are given with diameter thickness, thus in solving the area under shear, you just have to simply substitute the values, and then we get pi times 60 mm diameter times 5 mm thickness. Thus we get the value of the area equal to 942.6 millimeter square. Right? So now that we get the area under shear, now let's solve the force equal to punch a hole. So this equation is a manipulation from the equation of the uh, shearing stress. So kaya ba na matanong na ang tau is equal to P over A. Thus, in getting the force, you just have to simply multiply area times the shearing stress. And in this problem, we are given with the maximum shearing force or the maximum shearing resistance of the plate. Thus, we just have to substitute the value of solved area or the area resisting the shearing stress multiplied by the maximum shearing stress, which is 350 Newton per meter squared. So when you are solving this problem, please take note of the units and the consistency. Okay. So please take note here that the unit of area is 940 of the area is millimeter squared, and the unit for the maximum shearing stress is Newton per millimeter squared. Thus, if we are multiplying these two values, makuha na to aning answer is Newton. Right? So please be mindful. Please be mindful of the consistency of units. So kung pwede, most of it is you have to preserve the units when solving these problems para hindi mo makalimot, hindi mo malipat sa mga units. Okay? So let's continue solving this. Then evaluating this 942.6 times 350, so we got 329.10 newtons. Okay, or the final answer here is that the force required to punch a 16 millimeter hole with a thickness of 5 millimeters is equal to 329.91 kilonewtons. Okay, so this is our final answer. So this is the final answer of this problem. So we first get the area. From the area resisting the shearing load of 942.6 millimeters squared. And after that, since we are given with the maximum shearing resistance of the plate, we just have to simply solve the required force by substituting values. Thus, we got the final value of the required force 329.91 kilonewtons. Alright, so please do a review of the topics we have discussed here. The tensile stress and strain, compressive stress and strain, and shearing stress and strain. So these are only simple stresses, but please do a review and solve a set of problems. Solve a set of problems so you can practice. So you can learn how to solve particular problems in when a body is applied with shearing, tensile, or compressive loads. Right. So that is all for this lecture. In the next lecture, I'll be discussing about bearing or torsional stress and strain. So, and also we'll proceed with module 3, discussing further lessons on this course. Right. So please do a self-study by uh, solving a problem set. Might give you a problem set in machine design. So in your home, you can do a practice solving. Although I will not require you to submit. It's not assignment. I will not require you to submit your solutions out of that. Right. So that is all for now. Thank you for listening, and see you in our next lecture or meeting.